Yes, sir.
Okay, thank you, ma'am. So, good evening, all. Uh, so, this month we have conducted a IBIQ lecture series. It is organized by Indian Association of Physics Teachers, Sub-Regional Council of Pune, 08. And very nicely, we have conducted the two lectures. The first lecture was delivered by Dr. Ranjit Kashi. Uh, Second was by Dr. Vandana Luthra from the Delhi, New Delhi. And the today's lecture is again a very renowned scientist and researcher who is working in quantum science and quantum computing, Dr. Vikas Kashi. So, as we have started this series very in a short time, and I thank you, Vikas, for accepting our invitation and being ready for this today's lecture. So, Dr. Vikas Kashi will be speaking on quantum science and technology in a magnetism perspective. So it's a very new topic compared to the previous two topics, and it will be a continuation of the previous two sessions. So I request former President of Pune Sabasi, Professor Bharat Kangode sir, to introduce today's speaker. So over to you, sir.
Thank you. Thank you, Secretary Ma'am, Gorpade Ma'am, and today's speaker, as well as all my colleagues and teachers. It's a formal introduction of Dr. Vikas Kashid. Uh, it is with immense personal pride that I introduce a remarkable individual, Dr. Vikas Kashid. To many, he is a distinguished scientist and program head associated with cutting edge research in theoretical physics. To me, he will always first be that bright, inquisitive student who walked into my classrooms at Annasaheb Wagere College, Otur in Pune district, to have guided him during his graduation and to now witness the heights of his intellectual journey is a profound joy for me. Today, it is my privilege to connect the dots from his promising young mind in Pune's hinterlands to a global researcher shaping the future of material science. Dr. Vikas Kashid's academic journey is testament to relentless curiosity and dedication. Rooted firmly at Savitribai Phule Pune University, he earned a PhD in theoretical condensed matter physics in May 2014 from the Department of Physics, laying the foundation for his specialist group of the quantum mechanical underpinning of materials. Um, Later on, the Science and Engineering Research Board of the Government of India awarded him the prestigious Overseas Postdoctoral Fellowship in 2017. This has led him to the world-renowned Peter Grünberg Institute at Jülich in Germany. And here at Jülich, Dr. Kashid honed his skills and broadened his perspectives alongside some of the best minds in the field. Back in SPPU, at his postdoctoral tenure, he channeled his expertise into sustainable energy solutions. His work focused on the lead-free perovskite materials, aiming to engineer them for better efficiency. This research is crucial while perovskites promises next-generation solar cells. Their typical lead content poses risk. Dr. Kashid's computational work in seeking efficient, non-toxic alternatives places him at the forefront of the green energy revolution. Uh, Actually, his special interests lie in performing sophisticated electronic structure calculations of magnetic and topological materials. This is the key to advancing data storage and spintronics. Dr. Kashid, through his simulations, is a digital explorer mapping the electronic landscapes of materials that will define future technologies. Gathering his accomplishment paint a picture of a silent contributor to the edifice of science. His publications, fellowships, and affiliations trace the arc of dedicated physicists. Behind every publication is a persistent quest for clarity in the complex world of electrons and atoms. When I introduce Dr. Vikas Kasip today, I see both the past and the future, the diligent student from Otur who asks the right questions, and the confident scientist who now provides answers to the world needs. His journey from our college benches to the Germany's high-tech lab and back to the pioneering work in Pune is an inspirational blueprint. It proves that roots in the small town can nourish a tree that reaches for the global scientific key. Uh, he embodies the true spirit of learning to ascend, to explore, and to return with the knowledge that illuminates. It is a celebration of academic excellence, enduring mentorship, and the glorious promise of Indian science personified in a former student. Please join me in welcoming him with the greatest admiration and warmth. My ex student, a brilliant son of the soil, and a leading light in the world of theoretical physics, Dr. Vikas Kashi. So I welcome once again on the behalf of IIPT SRC as well as Central IIPT and request Dr. Vikas to go ahead for delivering his session. Thank you. Over to you.
Thank you, sir. Thank you so much for this kind information, kind introduction as well. It's really my privilege and honor to be here in this team and share my experiences, my work, my results. I'll try my best to keep it simple. Let me first of all put it in screen, full screen mode. Yeah. I hope the screen is visible now.
Yes, yes.
And it is my privilege as well, sir, that I was part of um, Otur College when you were faculty, and it was really my privilege to learn a lot of lessons from you. You were one of the most brightest inspirations to me that I pursued physics later on, and I do not hesitate to tell this multiple number of times. So thank you so much for being in my life and inspiring me all over my career to pursue fundamental physics. Um, Thank you, Shashi, for this very kind opportunity. And again, really great feeling to be part of this community, part of this family, and share my thoughts. So today I'll share my views on quantum science and technology. It's very broad area, very vast area, but I'll try to pick a small glimpse of or a small area of this area from a particular perspective, like magnetism perspective today, maybe from energy perspective some other time. And there are a lot of different perspective because people are working in this area in different dimensions. They are getting a lot of interesting results day by day, and we are actually exponentially growing our understanding like day by day in this particular area. So this is the outline of my talk. Considering that we have some undergraduate, postgraduate students as well today, I will try my best to keep the talk simple. I will not try to incorporate too much of mathematics or too much of complicated results as well. But let me try to connect one point to another point and then try to make all of us understand in a particular area. I'll try my best to build the connection of our fundamental understanding of the quantum theory of the magnetism that we know in textbook in our undergrad and postgrad as well, what we call as collinear magnetism. And then based on our understanding about the exchange interaction, which can be symmetric, antisymmetric, or even more complicated as well, let's try to take our understanding of magnetism from the conventional magnets like long range interaction magnets to some non-conventional magnets, and then let's try to bring the elements, very important elements called as rare earths, into the modern magnetic system. And from them I will try my best to introduce you all to a very new, very innovative type of magnetic particles called as cormions, and how they are really playing very vital role in today's spintronic devices, and how we can use our basic understanding of quantum mechanics and also the condensed matter physics to use these spintronic devices in day-to-day quantum technologies. To start with, I'll quickly go through like 4 or 5 slides to revise or recap our understanding about the magnetism. We know that 100 years ago, approximately in 1922, very famous historical experiment Stern and Gerlach, they heated silver atoms, so neutral silver atoms, when they allowed to pass through collimator, and the non-homogeneous, or let's say the magnetic field which is having non-homogeneous field applied on the particle, it was passed, the particles were passed through this non-homogeneous field. It was classically expected that we could have got a single spot, or maybe the distributed spots, equally distributed spots on the detector, but somehow it showed very crystal clear two spots on the screen or detector. That raised some questions, and it gave the origin or the conceptual understanding of the discovery of spin. And because of discovery of spin, the entire magnetism got revolutionized. The concepts of magnetism, the origin of magnetism, which was not able to like being explained with the help of classical mechanics, got some roots to understand it. So this particular experiment, first of all, made sure that there is another parameter called a spin associated with every particle, fermi ion, let's say electron, which cannot be understood on the basis of classical mechanics. It is purely intrinsic property, and it can be only explained based on the quantum mechanics. So this intrinsic property of the electron, which is called a spin, it is leading to the space quantization, number one, and also it is giving us a hint to measure the quantum mechanical property called as eigenvalue, which can be either plus half or minus half, depending on the external field, or depending on the global magnetization axis as well. So because of spin, the overview of looking into the quantum mechanical particle, quantum mechanical state changed completely. And then we started looking at the origin of the magnetism. So currently, if we talk about the intrinsic magnetism, let's say we are not talking about the magnetism when we apply the external field on any particle, right? We are talking about the intrinsic origin of the magnetism. Right now, other than quantum mechanical explanation, we can't describe how it is originated, how it is generated. We know that electron, when it is revolving around a nucleus, it generates a current, and then we have the associated magnetic field, then electric field, and lot of things are there. In classical textbook as well, we know that we can write down this magnetic Hamiltonian as long as the single electron as a particle is considered. So we know that we cannot separate out the kinetic energy and potential energy completely. We have to have the concept called as vector potential that is brought into the picture, and then we describe the total Hamiltonian in this particular way. I'll not go into the details because we have already studied this part. But the moment we talk about this moment, let's say orbital magnetic moment or the spin moment, we know that these are quantized and they have very fixed magnitude, fixed eigenvalues. And these particular numbers, they also can be considered when you incorporate them into the main Hamiltonian, let's say by using the Dirac's equation, or let's say relativistic expressions. We know that they can interact with the external field, and we can explain a lot of different phenomena. Because we have quantization in the orbital moment and also the spin moment, their interaction is also a direction dependent quantity, and the magnitude and the direction of this interaction decides lots of properties of the magnetic material. So today we know that this magnetism in material, it comes purely from the exchange interaction. So exchange interaction is the only reason that we can explain the magnetism in material. Like quantum theory of magnetism starts with exchange interaction. And where is this exchange interaction is coming from? It comes from two different parts. One part is Pauli's exclusion principle. We know that no two particle, quantum mechanical particle, can have the same set of quantum numbers. And because of that, the moment we try to exchange two electrons, the antisymmetric behavior of the wave function should be considered. Otherwise, we cannot do that. And the second reason is that Coulombic repulsion between the two different electrons. Coulombic repulsion is again purely a quantum mechanical phenomenon. We consider two electrons being the charged particle. They repel each other, even if we consider their spins as up and up down as well. So the relative repulsion between the two different electrons based on their spin lies, or the reason goes in the antisymmetric nature of these two electron wave functions. And combining these two properties, Pauli's exclusion principle and the Coulomb repulsion between these two electrons, we can explain the exchange interaction between the two, let's say, fermi ions or electrons, which leads to the let's say magnetism and exchange interaction. So essentially, if you have two different electrons, they will try to prefer to repel each other, and they will try to keep at different energy levels. So even if two electrons they are revolving around an atom, they will not try to like align themselves in anti-parallel direction, and they will try to minimize the energy. Energy is minimum when we actually separate them from each other. So based on this, we know that exchange interaction can explain now long range magnetic order, magnetic interaction. And what are the long range magnetic orders? We know ferromagnetic type, right? We know in ferromagnetic interaction, the magnetic moment from different atoms, they align parallel to each other, and the total magnetic moment of the entire sample, they just simply numerically adds to the number. And the alignment between the ferromagnetic in the ferromagnetic material is actually characterized by a parameter called as GIZ, exchange interaction parameter, which we'll see later on. But it decides whether the moment they will align parallelly or anti-parallelly. The moment they are minimizing the energy by aligning themselves in parallel direction, the arrangement is called as ferromagnetic one. And there are a lot of examples. We have iron, cobalt. Deliberately, I kept some numbers, names such as gadolinium, dysprosium, some rare earth metals, because these are the new generation magnetic materials. There is also another long range magnetic order called as ferrimagnetic. So most of the spins they align parallel to each other, but some spin they align anti-parallel. And because of that, the total magnetization of the sample is not the maximum one, but it is the difference between those parallelly and anti-parallelly aligned magnetic moments. Now, in the last couple of years, people have also started talking about ultramagnetism. In case you are also aware of that, in ultramagnetism, there is a competition between ferromagnetic and antiferromagnetic. Antiferromagnetic is also a long-range magnetic order, and the nearest neighbor interaction, and then next to next nearest neighbor interaction, they also play a vital role in deciding how the magnetic moment should be aligned with each other. In case of antiferromagnetic order, if you do the calculation for the entire crystal, entire unit cell, let's say, the total magnetization always comes to zero, because they are aligned anti-parallel to each other. So the total magnetization of the sample is zero. But if you let's say focus, or let's say zoom into a particular atom, you have very strong magnetic moment. And the interaction between the neighboring atoms, they try to minimize the energy by aligning them in anti-parallel way. Paramagnetic is one of the interesting pattern that we have. The every atom has some kind of non-zero magnetic moment, but they align so randomly that the total summation of the magnetic moment is actually counted to be zero if there is no field applied from the external side. But if you apply the field from the external side, then they align along in the direction aligned with the external field, and then you get some kind of non-zero magnetic moment. In case of diamagnetic, it is exactly opposite. They align anti-parallel to the external magnetic field, and we have a lot of examples as well. So all these magnetic materials, they are sustaining their magnetism based on the long range order, except this paramagnetic and diamagnetic, where the interaction between one magnetic moment and another magnetic moment is relatively weaker compared with ferro, ferri, or antiferromagnetic order. And now coming back to our understanding how we can talk about the exchange interaction. So exchange interaction is the Hamiltonian. Actually, if you write down the Schrodinger equation for all the atoms in a picture, like let's say in a crystal or in a unit cell, usually this Heisenberg interaction is not automatically incorporated. We have to incorporate this based on intrinsic interaction coming from the atoms, or intrinsic interaction between the electrons as well. So this Heisenberg exchange interaction is denoted by summation over all those particles, all these places, Si dot Sj. Si, Sj are the spins on two different particles, and Giz, it indicates the interaction parameter. Depending on the orientation, now we look very carefully. This is Si dot Sj. So two vectors, they are in product with scalar product kind of pattern. So definitely the angle between these two vectors matters a lot for us to understand whether it can be a linear, collinear, or non-collinear magnetic order. So direct exchange, which is a direct overlap of the charge density from one atom to other atom, it tries to minimize the energy, and then we may get either ferromagnetic or antiferromagnetic magnetic alignment. In case of super exchange, we have mediating atom. So let's say manganese moment from one atom interacts or communicates with the manganese moment of another atom through a mediating atom which is non-magnetic, which can be oxygen or which can be some other atom as well. Most of the time, the super exchange interactions, or let's say hopping interactions, they are usually antiferromagnetically aligned so that that reduces the total energy. There is third one, which is called as itinerant exchange interaction, which is observed in mostly in metals, because in metals, the outermost orbital electrons, they are free. They are relatively carrying low energy, and they can be polarized with respect to magnetic moment of the atom itself. And the moment external field is applied, all these free electrons, they carry the magnetic interaction. They are relatively weaker, and most of the metals, magnetic metal, they can be explained. The wave function of these electrons is highly delocalized. So they overlap very easily from one atom to other atom, and this phenomenon can be explained. Here is something interesting. Now we know that if we focus on this expression again, Si.Hj, we know that the maximum amount of energy can be minimized looking at the negative sign again when the two magnetic moments, they are aligned parallel to each other, right? Si.Hj. If the angle is 0, cosine of 0 is 1. So we get maximum energy, and that too having negative sign will be more and more negative. For us, the stable system is the one when we have minimization of the total energy, like maximum negative number we should hit, so that we can say relatively it is stable system. Considering here, what if that the two magnetic moments on two different atoms, they are not aligned parallelly. So they are aligned anti-parallel to each other. So definitely cos of theta will be less than 1. So the energy might be higher than the collinear configuration. But are these non-collinear configurations stable? Are these observed in real systems? That we'll try to find out. So in this case, in case we have two magnetic moments which are not parallel and they are aligned having some kind of angle between them. In that case, there is another kind of exchange interaction which is contributing to the Hamiltonian, and that is called as antisymmetric exchange. It is also called as anisotropic because in this case, the direction dependent energy is actually different. The moment we change the direction of two spins on two different atoms, we get different amount of energy. So in this case, because of the different energy, it is also dependent on theta, relative angle between them. And antisymmetric exchange interaction, it is calculated by taking the cross product between the spins, Si cross Sj, with the magnitude is given by Dij. Now, what if we get some kind of non-zero number from this contribution? Yeah. Even if we get non-zero number, it is also possible that it can be destroyed by a lot of different interactions in the system itself. First of all, we know that there is a magnetocrystalline anisotropy. There is an isotropic exchange. Isotropic exchange is again the energy coming from the Heisenberg interaction, where the spins are always preferred to align parallel to each other. So if there is a minimum energy required to align these spins parallel to each other, definitely such kind of pattern will be immediately be disturbed. They will not contribute, or they will not be sustainable. They will be destroyed, and such kind of spin orientation will not be important for us. But if the energy contribution, which is I'm writing down as EDM, I'll tell after some time what this DM is actually. But if this EDM is having this sizable magnitude compared with the isotropic exchange or the Heisenberg exchange, and if it is larger than the magnetic anisotropy energy. Now, what is anisotropy energy? Again, we have the moment we try to orient the moment in an atom in different directions, we get different energies. Yeah, and it is totally dependent on the symmetry of the lattice, symmetry of the system, symmetry of the crystal, symmetry of the unit cell as well. And if it is having the same energy, doesn't matter how we are orienting, in that case, there is no magnetic anisotropy energy. But if it is dependent on what direction the magnetic moment is oriented, and if energy is changing, then definitely again, the nature will prefer to orient all those magnetic moments in that direction where the energy is minimum. Now, the amount of energy required to rotate from one direction to another direction, we can compute this in the form of magnetic anisotropy energy. And if this contribution coming from the antisymmetric exchange, it is competing very well with the Heisenberg interaction, magnetic anisotropy energy, total together. In that case, such non-collinear structures, non-collinear magnetic structures can sustain, can exist even at low temperature or even at room temperature. So basically, when I observe such kind of magnetic structure exist in the ground state, I can say that Heisenberg interaction, which is coming from the Coulombic and antisymmetric wave function, or even we can add the Hubbard interaction, which is coming from the hopping of the electrons. If it is smaller compared with this non-collinear alignment of the magnetic moments, then we can get some kind of achiral structures. Now, achiral structures doesn't mean that we can have random orientation of the magnetic moment, which is very similar to what we were considering in paramagnetic system. Right now, we are talking about an really ordered homogeneous magnetic moments throughout the lattice. And if you see that even if one magnetic moment and another magnetic moment, they are rotated even by smaller angle of theta, yeah, the same magnetic moment can be repeated after very long interval of the space. That maybe we can say the longer wavelength. And after longer wavelength, we can still get the same magnetic moment. So between this moment and the last atom where we are getting the complete wavelength measured, the moments of the consecutive atoms, they are rotated by the constant angle theta. And in one line, you can refer this figure, the last figure. If we have a collinear atom chain, in that case, you can see that the rotation gives like a kind of a, let's say, spiral or chiral chain of the spins. If you consider one-dimensional system mapped to the two-dimensional system, you can find out such kind of very interesting flowery pattern where each arrow which I have shown here indicates the total effective magnetic moment on one atom. So if you see a surface of atoms, then you can find out such kind of flowery pattern or such kind of interesting circular or some kind of, let's say, elongated pattern of magnetic moments where they rotate in a homogeneous way. There are also non-homogeneous patterns as well, but homogeneous patterns are more useful in spintronic devices because quantum technology is traveling towards the minimization of total energy. It is not very easy to handle when the magnetic moments are not aligned in a homogeneous way. So here is the actual picture where if you pick up one arrow on the site of every atom and see the total picture of the magnetic moment orientation in those system. So do such chiral magnetic interaction exist in reality? So this was the experiment when I was doing my PhD, and the group in which I worked during my postdoctoral research, they have done this experiment in the laboratory, and it was published in Nature at that time. And it started completely new era about people talking about this non-collinear direction, non-collinear magnetism. So let me explain what this experiment is very, very quickly. In the picture A, you can see that there is a tungsten surface, and on the tungsten surface, we have manganese, one single atomic layer, exactly single atomic layer of manganese on tungsten 110. And then they measure the magnetic alignment of all this tungsten atom by using spin polarized scanning tunneling microscopy. So the tip was scanned throughout the sample, and then the magnetic orientation was actually measured. So looking at it very carefully, the picture B is the actual outcome. So if you see that there is a very dark line and then followed by bright line, dark line, bright line. So we can say that the magnetic moment is actually flipped. So because being the tip at like magnetic tip, let's say it can be of specific atom as well. The tip interacts with the atom at the surface, and based on their mutual interaction, we get some kind of constant current measurement in the STM experiment. So we see that the bright line, if we assign this to be equal to the spin up in the layer, the dark line indicates spin down layer, and so on. So initially, it was interpreted that it is an antiferromagnetic system, very planar antiferromagnetic. So if you travel on one direction, all the atoms, they carry spin up. The moment you travel along y direction, all the atoms, they flip the spin, and so on. So this was the picture. But look at the plot which was shown in the downmost part. It shows some kind of corrugation. So amplitude of the spin was not uniform throughout the pattern. So they predicted that it can be two different things. One is that it can be a spin density wave, or it can be a spin spiral wave. Now, spin density wave, what is spin density wave? We have the magnetic moments align parallel and anti-parallel uniformly. There is no doubt about that. But the magnitude of magnetic moments can be oscillating. So in that case, you see a ferromagnetic pattern as ferromagnetic or antiferromagnetic pattern as antiferromagnetic. But the amplitude of the moments will be oscillating. In that case, you see that there is a brightness and darkness, which is observed in plot number B. Somehow they verified this by another experiment, which is given on the right hand side. They changed the orientation of the magnetic moment, which is placed on the tip of the STM tip. Yeah. So the orientation and the field, that initially it was applied with 0, then 1, and then 2 Tesla. And with these three different magnetic field and also the orientation, you can also see the arrow, the way it is oriented. So they got these three patterns, again A, B, and C, which is given on the right-hand side. This is field-dependent spin polarized scanning tunneling microscopy measurements. What they were expecting, if this was the pattern which was on the left-hand side given as in the B, if this was a purely spin density wave, then irrespective of the applied field and also irrespective of the moment, orientation of the moment on the tip, the spin density wave should not dislocate. You can refer any that spot that you're observing here and see the brightness and the darkness observed with respect to that particular point. You can focus on any point. You can pick up any coordinate in that particular plot and see how they are changing. So if this was a spin density wave, the brightness and darkness spot should have occurred at the same place. Somehow, because of the change in the field and change in the magnetic moment, and they observe that now the brightness pattern is actually shifting from one side to another side. And this is purely because of the interaction of the magnetic moment, which is placed on the tip along with the surface. So the atom with the surface. So these two atoms, they interact with each other. And because of this interaction, the brightness and darkness pattern is actually changing, indicating that the magnetic moment, even if they are appearing to be like different intensity, they are not actually intensities, but they are actually rotating, because the Si dot Sj, again the interaction energy coming from Si dot Sj, the angle between the magnetic moment of the tip and magnetic moment on the surface atom, they are actually changing. Because of that, the strip, they immediately got changed their location on the pattern, which ensure that this is the spin spiral wave. And this was the first ever experiment and in the laboratory proven that magnetic structure, even at room temperature, people can observe such kind of pattern, which is away other than ferromagnetic and antiferromagnetic. So far, conventionally, we were identifying magnetic structures as either they can be ferromagnetic or antiferromagnetic, or maybe diamagnetic and paramagnetic, though they are not very important to us as long as the long range order is concerned. But this was one of the most pioneering and breakthrough experiment that they prove that chiral structures can exist. Where other places we can expect the chiral structures? This is again a real image, STM image, which was published later on. And people then realize that we have very conventional, like very from old ages as well, we know that we have magnetic domains, where in one particular domain, the entire structure, like crystal structure, all the group of atoms, they are oriented in one particular direction. The moment you go from one domain to another domain, the total effective magnetic moment changes the direction. So what happens exactly at the boundary? So people, they did some kind of experiment, and this was done by the simulation by using quantum mechanical calculation with the incorporation of the spin-spin interaction, which also showed that the system will try to minimize the energy only when there is a transition of the magnetic moment, direction of the magnetic moment from one place to another place, consequently and sequentially as well. Like it goes in a chiral way, then only it minimizes the energy. If it is not going in that particular way, then there is high chances that due to the spin frustration, the system will try to increase this energy. And because of the ground state structures and this particular structure to exist at room temperature or low temperature as well, the domains, they prefer to have this chiral rotation of the magnetic moments in those patterns, which is also verified later on by in the experimental setup. So to understand how these magnetic interactions they are actually considered, we know that there are certain models through which we can compute the numerical interaction energy. We can also understand how the long range interaction can explain a particular magnetic structure in a sample. Let's say we have the conventional Heisenberg model, which is one of the oldest model in understanding the long range magnetic interaction in materials. So we know that the total eigenenergy or energy of that particular interaction can be computed by calculating Si dot Hj with Jij as the interaction parameter, Heisenberg interaction parameter, whose value and the sign decides whether this interaction can be ferromagnetic or antiferromagnetic. If the interaction is very strong, the dominant interaction mostly comes from the nearest neighbor. In antiferromagnetic cases, the next nearest neighbors also contribute. And the cases where we are right now discussing or we are interested, the spiral structures, where the long and long range interactions, they also try to dominate. So nearest neighbor interactions are actually less dominant than the next nearest and next to next nearest neighbor interactions. So I personally calculated these interactions when I was talking about, considering the Magnon interactions. I realized that until sixth and seventh neighbor, these atoms actually contribute very significantly in the calculation of the Heisenberg interaction parameter. And obviously, we have already studied this in the textbook that depending on the sign of Giz, we can decide whether the interaction leads to a ground state which is ferromagnetic or antiferromagnetic in nature, whether it's J1 is positive or J1 is negative. Again, it may happen that the nearest neighbor interaction may be positive, the next nearest neighbor interaction might be negative, and again further interaction might be also positive or negative. So then, in such cases, we have to understand the competition of all nearest neighbor, next nearest neighbor, next to next nearest neighbor interactions, and find out, is there any frustration or is there any kind of effective interaction that leads to some kind of interesting magnetic ground state as well. So here is, I just present one of my calculations where we have calculated this isotropic exchange interaction. So Heisenberg interaction, we are calling as isotropic. Isotropic in a way that the moment the angle between two magnetic moment is fixed, I actually do not care how they are oriented. So they may be oriented with some angle of angle with respect to the global magnetization axis. But as long as the magnetic moments, they are aligned parallel to each other, the interaction should not have different amount of energy. And it is plotted here for a particular chain. You can see this chain. I have not given the details of this calculation because I thought this might not be totally of interest of this community, but I will quickly give you the idea. When we do the calculation for ferromagnetic order, we just need a typical unit cell to calculate, and we apply the Bloch theorem. So Bloch theorem and using the expansion of wave function in terms of the plane waves will take care to keep this image everywhere of this particular lattice, and we get the wave functions mapped at the boundary of the cell. So that's how we do the calculation for ferromagnetic cell. The moment you want to calculate the antiferromagnetic cell, because of the periodicity of the lattice or because of the chronic penny model that we are applying there, we try to prefer to have anti-parallel spin alignment in the calculation directly, so that everywhere it is anti-parallel. In case we have to try for antiferromagnetic in a particular direction or in a lattice or in three-dimensional space, we have to arrange accordingly. How many number of supercell, how many number of atoms we have to incorporate in a cell, and then compute the total amount of energy. Now here, in order to accommodate these many different rotations, we cannot actually afford to have larger and larger number of atoms with different spin orientation in a single unit cell. Because the moment you try to incorporate more and more different orientation of magnetic moment in the cell, your actual number of atoms to be calculated becomes very huge. And to tell you, I think a lot of people here can be having the background of DFT, but to solve a particular Schrodinger equation, we do not have an exact solution. We do it iteratively because we start with a guess electron density, we minimize it, we minimize the Hamiltonian, we minimize the potential energy as well, and we'll end up with some kind of the ground state energy. And that ground state energy, we have to, in order to get that ground state energy, our Hamiltonian actually operates on the wave function 1,000 number of times for multiple different interactions, and then we get the total amount of energy. The moment we increase the number of electrons, because it's a single particle calculation, the moment we increase the number of electrons, the calculation increase as to the power n. So it is actually higher order complicated number of calculations we have to do. So we try to use the Bloch theorem that we apply for a general calculation, but we also include the spin in the general Bloch theorem, where spin moment can also be considered by keeping an angle theta and add one spinor, put in the Hamiltonian, get it solved. So this is how the outcome of that particular calculation. But I'll be happy in case someone is interested to know exactly how this calculation is done, because otherwise we have to incorporate the entire cell, entire probabilities of all the rotation of magnetic moment into the system. But this is how the calculation is done, and because of this symmetry, I have not shown both the angles, both the sense of rotation. So if I had to change the rotation of magnetic moment in one particular direction, and if I change the direction only, like sense of rotation, let's say if I consider the axis z, and if I change the theta for minus theta as well, the energy should be same. Again, going back to the same expression, si dot hj, cos of theta is even function, so I do not actually care a lot where I change the first spin with respect to second spin in a positive direction, like let's say counterclockwise or clockwise direction. They should produce the same number. And to understand this plot, this q is equal to 0 indicate that there is no rotation. So theta should be 0, indicating that they are ferromagnetic. and the maximum number is 0.5. So this Q is actually the transformation of Fourier transformation of your real space to the Fourier space or reciprocal space. So Q is equal to 0.5, indicating that the another spin actually rotates by 0.5 in the z-axis. So it indicates the antiferromagnetic direction. And all these the microscopic points of Q that I have considered, they indicate that rotation of the magnetic moment from one to another direction through a sequential change of angle theta. And this is homogeneous one. So if I consider this atom is having like oriented in vertical z direction, if there is a theta, the theta is maintained from this second atom to third atom, the theta is maintained from third to fourth and so on. We also tried this non-homogeneous calculations, but we realized that homogeneous calculations are naturally more favored, energetically favored. They try to reach to the ground state energy more easily. So here, if I consider, you'll notice that all these structures, they prefer to go for ferromagnetic configuration. But if you look very carefully, this pink color curve here on the right hand side, which is given by cobalt platinum set of atoms, and on the left hand side, this blue color curve, which is again iron platinum, they have the ground state energy little away from the ferromagnetic state. So there is an energy gain here and also here, even if it is not much. On the left hand side, the numbers are in millielectron volt. They are extremely small, extremely low energy calculations we have done, which indicates that the gain in the energy can actually overcome the isotropic interaction, indicating that there is a possibility that these two structures can have chiral state. And this chiral state we have to verify. As we have already discussed a couple of slides before, that this is not the sufficient condition that we get this interaction having the energy to win the chirality. It has to compete with isotropic exchange and also the magnetic anisotropy energy. Right now, it does have compete with the isotropic exchange. So definitely, I can say here that these two structures may be leading to the chiral interaction energy. But let's understand some other part as well. The story is not completely over. We have not yet won the situation or the, let's say, even the competition. There is another term which is called as magnetic anisotropy. So magnetic moment in any material, they prefer to align along a particular direction, and we always call it as a easy axis. Now, easy axis can be and completely dependent on the symmetry of that particular crystal, particular lattice as well. So if the cubical symmetry is there, then preferably easy axis goes along one of the easy direction, which is like Cartesian axis. If the crystal is octahedral symmetry, if the crystal is, let's say, tetrahedral symmetry, then based on the symmetry, the easy axis can be different. And we can actually gradually change the orientation of magnetic moment from, let's say, z direction, which is our global magnetization axis, to any other axis, and calculate the energy as a function of theta. And we realize that we get very interesting curves, and based on the curves we can find out what is the z-axis, what is the amount of energy that is required if you really want to move the moment from one particular direction to other direction as well. And for cubic system, uni-axis system, again, maybe postgraduate students and PhD students, they can also realize that this is the part of their, let's say, quantum solid state physics, that we can get this amount of energy based on theta and the parameter K1, K2, blah, blah, blah. So not going into the detail, the thing that I'm trying to pick from here is that magnetic anisotropy energy is always there as a safeguard, which will try to orient any magnetic moment which is not aligned along the direction of the global magnetization axis to that axis again. So any randomly oriented moment, the anisotropy energy will try to bring it back. So anisotropy energy is again just like a guard there. If somebody is not following the order, he'll try to bring to the disciplined order again. But what if the amount of energy we have gained because of the non-coherent moment is still competing with this as well? So if he has enough energy to fight with the magnetic anisotropy energy, it will still win the job. And this is how the case. Now, magnetic anisotropy energy, it does not come from a single term. It has a two contribution. Again, this is a part of our basic fundamental physics. The first is dipole-dipole interaction. Dipole-dipole interaction is like energy between the interaction of two dipole moments from two different atoms. How they are interacting, how they are related to each other. First thing is that the distance, how far they are located. Then the second is what is the magnitude of magnetic moment on each atom. If it is extremely strong, then maybe dipole-dipole interaction can be significantly contributing. If the distance between these two magnetic moments is very far, then perhaps they will not contribute. So two magnetic moments should be strong enough. They should be close enough. In that case, dipole-dipole interaction energy can be strong. This is one of the contribution to magnetic anisotropy energy. Now, Again, even if it is strong, the contribution of magnetic anisotropy energy to the total energy is in the range of 10 to the power minus 4 eV, maybe some milli eV to few hundreds or few decades of micro eV, we can say. And what is the role of this magnetic anisotropy energy? If we consider a planar structure, let's say thin film or a single atomic sheet of some kind of magnetic material, it tries to prefer that all the atoms they put or they try to orient their magnetic moment in the plane. Because the moment a magnetic moment is out of the plane, the energy is very high and it is very easy that it can be polarized by external magnetic field. So to orient those magnetic moments, it prefers the dipole-dipole interaction takes care to align all those magnetic moment to lie in the plane itself. I mean, exceptionally, sometimes it is also out of the plane, but in those cases, then those materials are very, very special, very, very separate. But otherwise, it tries to prefer to align in the plane. Second thing is that if you have elongated nanostructure or elongated quantum mechanical structure where we have very few atoms, but they are in a uniform elongated uh, pattern they are arranged. So in those cases, the magnetic moment of all the atoms, they prefer to follow the longer axis because again, it minimizes the energy. The moment they are oriented outside the axis, then it is very easy to break this anisotropy energy and again destabilize the structure. So to stabilize this structure in a ground state at any temperature, even low temperature or even at room temperature, it is easy that magnetic anisotropy energy will try to align all this magnetic moment either in the structure or along the longer axis. So this is one of the ways that it plays a very important role as a magnetic anisotropy energy. There is a second contribution coming from. The second contribution is really, really important. That is magnetocrystalline anisotropy. Where it is coming from? It comes from the spin and orbit coupling. Here we have more quantization effect to play a very important role. The L is quantized, S is quantized. And then the interaction between the spin magnetic moment and orbital magnetic moment, the interaction and the let's say magnitude of this interaction decides the anisotropy energy of this particular structure. So if spin and orbit interaction is extremely anisotropic in a particular structure, then we have very strong magnetocrystalline anisotropy. And this anisotropy will not at all allow any randomly oriented magnetic moment, which is not disciplined. So it will try to bring along the easy axis. And this has to compete with the energy gain that we are getting from the anisotropic interaction, or let's say antisymmetric exchange interaction that is coming in the solids. And this is having very strong magnitude. So this particular contribution coming from magnetic crystalline anisotropy is orders of magnitude larger compared with dipole-dipole interaction. So if you really compare dipole-dipole interaction and this magnetocrystalline anisotropy, we can easily or safely ignore magnetic anisotropy energy coming from dipole-dipole interaction and only consider this because they are orders of magnitude higher compared with the previous one. So what happens that this comes from spin orbit coupling, and we know that spin orbit coupling again we can extend our Schrodinger equation to Dirac equation by incorporating these terms where we have the interaction between field and let's say the moment of the electron, which if you decompose this, we can say that this is nothing but the gradient of the potential, which is varying as a function of r from the nucleus to the outside. So it all depends where your electron is sitting in the atom and how the distribution of the potential with respect to the nucleus or with respect to the position from the center is actually concerned. And because it is dv by dr, this particular term sigma dot L is actually the spin and orbit interaction. However, look at this particular term, which is giving you the magnitude of the interaction. This is dv by dr, which is a function of z itself. So the atom, when the atomic number is higher, let's say if you compare the lithium, sodium, potassium, or let's say carbon, these low Z atoms, and compare it with high Z atoms, let's say gold, silver, or even platinum, or even like all the atoms which are above in the periodic table above the iron atom, they have very high contribution to this interaction energy, which is coming from the spin orbit coupling. And its derivative is also larger for heavy atoms. So obviously, all those heavy atoms, if they are involved in your system on the surface or in your crystal, then they have very strong contribution to the spin and orbit coupling. And they are treated very specifically. So it is not easy to calculate this spin orbit coupling at a stretch in a Hamiltonian because because of its nature, which is non-linear nature. So we treat the spin orbit coupling only in the muffin tin, where we consider that we can expand using the atomic orbitals in the muffin tin. Outside, we use the plane waves. We neglect outside because as R increases, we can ignore that the term is not contributing significantly to this particular term. Anyway, but considering spin and orbit coupling, we need to understand it comes because of the high Z value. And those elements which are heavier, they have very strong spin orbit coupling. Now, spin orbit coupling, again going back, leads to the magnetocrystalline anisotropy, and this magnetocrystalline anisotropy is a major contribution to magnetic anisotropy. Magnetic anisotropy, going back again to this competition here, we have isotropic energy contribution coming from the Heisenberg interaction and the magnetic anisotropy energy. So these both together will try to fight with the contribution coming from the antisymmetric exchange. And here I'll try to incorporate a new word. This anisotropic exchange that we are talking so far, it is called as Januszewski-Moria interaction. It was after the Moria scientist who actually introduced this term in 1970s, but Januszewski later on proved on theoretical grounds as well as experimentally as well. This is very, very special interaction called as DMI, Januszewski-Moria interaction. These are two scientists, and they come from, look at here, S cross, or SI cross SA, like cross product of these two terms. And now, because we have cross product, we know that if two vectors are in a plane, right, their cross product will always lie perpendicular to the plane. And if we consider two different, let's say, spin rotating in a particular sense of rotation, and we don't have a spin orbit coupling. So spin orbit coupling here plays very important role to break the symmetry. Look at the picture which is shown in the maybe this cartoon in the upper side. So if you focus on, let's say, one block considers, or one block denotes the magnetic moment on one atom. If you travel along this q direction, look at here. So this is actually along one particular direction. The rotation is giving you a sense as if like the rotation is like, you can consider by taking the thumb, right? So it's perpendicular direction. If you consider here, the lattice R is here. I mean, the rotation is along the R axis basically. So in the second case, if you consider the flat spirals, then the rotation axis is vertical axis. And in the last case, it is along the right direction of the particular lattice. If it is not considering spin orbit coupling, okay, all these three different rotations, they contribute to the same magnitude, by the same magnitude, to the Heisenberg interaction energy, because there is no breaking of the symmetry. However, the moment you give some kind of platform, and now you consider the rotations with respect to this S0 cross Sn or Si cross Sj, doesn't matter. And this particular contribution, when you consider spin orbit coupling, because direction dependent, it is extremely sensitive and it breaks all the symmetries. And direction dependent, the moment you change the sense of rotation as well, the amount of energy involved is actually different. So if you solve this problem, we realize that Q being the rotation vector, if you change the sense of rotation, the energy actually changes the sign. And this breaks lot of important symmetric operations. So how to calculate this? I'll not go into the details of this slide once again, but if you want to calculate the strength of DMI or strength of antisymmetric exchange interaction, we perform, first of all, the collinear calculations. We neglect this spin orbit coupling because the total contribution of SOC is, let's say, some milli electron volt compared with the electron volt or few hundreds of electron volt of the total energy of the system. And we obtain the eigenfunctions for spin up and spin down separately, but we do not consider the spin orbit coupling. And then we calculate the first order perturbation of treating this spin orbit coupling for the entire Hamiltonian, spin orbit coupling Hamiltonian, for all the up and down states. And then we calculate the total energy of that particular state at a particular momentum vector, and also the point at which we are interested. And then we integrate the entire Brillouin zone to get the total interaction energy. And look at here, our red color equation, the total energy is the summation of the Heisenberg interaction energy and also the interaction energy coming from the antisymmetric nature of the wave function. This total energy should be lower than the ferromagnetic state, which we were discussing here. So in case we are really deciding whether this particular point is a non-collinear or not, the energy gain at this point should compete with both the energies that we are talking here. Yeah, and then I'll show you one of my calculations here. So the same calculation we are referring right now, FEIR and FEPT. So this is bit like entire brilliant zone we have considered. So here you can consider the red color curve here. So red color curve is isotropic exchange interaction coming from the Heisenberg interaction. So no antisymmetric interaction is considered, only symmetric interaction is considered. So here and here, there are 2 points where we have degeneracy in the eigenstate, where we got some kind of ground state. Also here, we did not get any ground state away from the ferromagnetic state, but after you add this blue color curve, which is coming from the antisymmetry, the degeneracy is completely lifted. And the blue color curve is the final total energy curve. Now, this blue color curve is away from zero. Zero, we understood that this was a ferromagnetic state, right? And again here as well, the black color curve, which is away from the ferromagnetic state, we get very huge amount of energy gain. And we proved theoretically that these particular structures among various structures actually that we scanned, these structures give rise to a chiral magnetic order at a ground state. Ground state essentially we mean that at 0 Kelvin, because this particular structure which I'm displaying on the slide right now, it may get destroyed the moment we bring the system to the room temperature, because the energy gain is approximately 10 millieV. We had 25 millieV energy gain the moment we bring from 0 Kelvin to the ground state, 300 Kelvin, let's say. So this may get destroyed at room temperature, but we have other structures which are even robust at the room temperature by getting this energy gain because of this antisymmetric energy gain. And there are some further parts which you can ignore right now, because we are not going into the detail why it is coming, which atom, which orbital, what interaction is actually contributing that. But you can see the rotation is so small, because this theta that we are talking, if this is 0, 0 is magnetic, ferromagnetic, and 0.5 being the antiferromagnetic, this is very close to the ferromagnetic structure. So the relative angle between two magnetic moments is really, really small. So that gives you the spiral waves with the wavelength of 51 angstrom. 51 angstrom is hardly 5 or 6 atoms separated from each other. Maybe you can keep 5, 6 atoms and you get this much of distance. And another is 36, which is even shorter one. So now coming back to the contribution from the spin orbit interaction, we see that these are the typical electronic band structures. Again, ignore certain parts. I will only pick some important points. Not go into the details of this calculations again, but let's say we have the electronic bands or electronic energy shifted because of this spin orbit coupling interaction. And we know that spin orbit coupling interaction is extremely direction dependent, also the position dependent in the Brillouin zone in the Fourier space. Not all electronic bands are actually affected, but certain bands are affected. And in the particular structure, bands have contribution coming from multiple orbitals, multiple atoms, multiple quantum numbers as well. And because it is an interaction between orbit and the spin, right? And orbit and spin relative orientation coming from a particular atom, again going back to the same expression where we wrote that it is dVr by dr, and it is extremely dependent on the Z, the atomic number of a particular atom. We know that these particular bands, if we diagnose it further in detail, these particular bands where you see those red and blue shifts a lot, they are coming from the heavy atom. So this particular system is iron and gold. Gold is heavier one. So the box which you are seeing right now, it is contributed by the gold atoms, and that to like d electrons, which are sensitive to the spin and orbit interaction contribution. And you can see this Lorentzian transformation that we have done for this particular data. It shows that a specific atom, a specific electronic levels where the spin and orbit interaction have more and more magnitude, they contribute significantly to this part. And we show that this is one of the reasons that why we are getting stable, non-destroying or they are very robust against the external magnetic field, such kind of non-collinear magnetic structures. I think I have some time, yes. So coming back to this particular magnetic moments, so far we were talking about the magnetic atoms, which are conventional magnets that we have considered so far, iron, let's say cobalt or nickel, manganese, chromium, some kind of system. People are more into investigating the magnets which are not conventional magnets, the magnets which are coming from, if you look at the periodic table, we have those last two series, lanthanides and actinides. Even if radioactive, but those atoms which are giving some kind of magnetic moment, they are extremely strong magnetic moments. The issue is that they are not classically defined as magnets, because we have the definition of magnets as the non-zero magnetic moment at room temperature. And room temperature, let's say for example, gadolinium has exactly half field shell, and because of exactly half field shell, the total magnetic moment coming from the gadolinium is one electron in each 4f shell. 4f shell is 4f15 or 4f14, so it accommodates 14 electrons, 7 up, 7 down. In case of gadolinium, uh, every block is filled by one half electron. So we have 7 Bohr magnetron coming from each and every single electron, because it is not having any down electron to nullify the magnetic moment. So the benefit of having gadolinium is that we have very strong magnetic moment per atom, basically. And they are having order in temperature close to the room temperature. So if you alloy this atom along with some other atom, which can give some kind of additional stability, this can be one of the best magnets in the spintronic devices, and you can have really strong magnets even coming from a small number of atoms, like rare earth atoms, and they can have very fascinating spintronic properties. However, these particular magnets need to be handled really carefully, because in a way, carefully as in like physics wise, because we need to understand their magnetic properties in a different way, because they do not come under the category of itinerant magnet, just like we were discussing the magnetic properties coming from the metallic atoms. Here, the magnetic moment is extremely localized. 4f electrons is one of the difficult problems to solve, and even like at this point, to the best of my knowledge, theoretically, there are hardly 6 to 7 groups in the world. They are able to handle these problems, and again, they are not very accurate as well. And the difficulty lies in the situation that this 4f magnetic moment do not interact with the another 4f magnetic moment in a direct way, right? So they follow this RKKY kind of pattern, where these 4f moments, they interact with local S and P electrons. These local and S and P electrons, they communicate the message from one 4f electron with another 4f electron of another atom. So it is like indirect exchange. So they communicate through a mediating atom, but this is not again super exchange kind of thing. They are completely different, and they're extremely localized. So their wave function is so localized that they hardly overlap with the wave function of S electron or wave function of P electrons, and that's why it's extremely complicated. But still, somehow, to some extent, we could have control to get these numbers. And to tell you very interestingly, that we could calibrate all these magnetic properties people are able to measure in the laboratories. We could find out by modifying our Hamiltonian properly, incorporate some interesting terms, and we try to find out these magnetic properties. They match really, really well. So what is interesting here, that this is a checkerboard antiferromagnetic ground state system, and this is how we modified by calculating the mean field approximation, or even we can say the dynamic mean field approximation, RPA. We try to find out their temperatures, order in temperature, and it matches really, really well with the experiment, so that we can understand the magnetic ordering in detail later on. So here is one interesting picture. Let's say we talk about a structure who has antiferromagnetic ground state in one direction. So what if we have lattice? In one direction, it goes as antiferromagnetic. If you consider another direction, it also goes as antiferromagnetic. So what if both the solutions, they do exist at the same time? So what we say, that as per the basic understanding from our Schrodinger's equation and the mechanics, that if there is one solution which is solution of Schrodinger equation, and if there is another solution which is also solution of the Schrodinger equation for a given set of potential energy and given set of the problems, let's say the particles and everything, we say that the linear combination of these two solutions is also a solution, which also incorporates some interesting pattern. So looking at this pattern, let's say we have antiferromagnetic checkerboard structure, which is two-dimensional plane. And if you consider the antiferromagnetic direction in one particular axis, let's say x-axis or y-axis, you try to find out the linear combination of these two axes. So the linear combination will definitely orient along the diagonal side or the hypotenuse side. And if you consider those, that also can be considered as one of the solutions. This leads to such kind of 3Q structures. So this is a typical antiferromagnetic. So if you consider any two atoms, they are actually antiparallelly aligned if you see very, very carefully. And still, this is the non-Coulombic structure. So this non-Coulombic structures also has another reason or another origin, that maybe collinear ground state, if you keep on adding their linear combinations, also gives rise to another frustration or another possible ground state, which can be even lower than their collinear structures as well. And we found that for this gadolinium or all those rare earth metal structures, they prefer to have such kind of ground state which is non-collinear. Now, being non-collinear one, you get a lot of interesting, fascinating properties later on as well. And being not, let's say, Holmium atom is again in my entire life, I found it one of the difficult system to actually control on in the context of designing the model Hamiltonian and getting the total eigenvalue and eigenenergy. I still could not get the exact correct energy, though I have reached to very close to the what experimentalists are observing, but still I am very far from that. So my point is that holmium itself is ground state itself is helical one. Can you imagine if you have helical ground state and if you have control on that magnetic moment to orient in a particular direction by mixing alloy, by mixing with some other elements, and you have a complete fundamental understanding, theoretical understanding that which interaction is contributing to what kind of energy, we can actually propose a lot of different structures to the industry, to let's say to the society, and we can bring a lot of interesting structures where these structures are actually going on. Um, okay, I'll take another 4 or 5 minutes maybe. So let's say skirmions. This is one of the examples, skirmions. Skirmion is one of the structures. Now you can actually easily correlate what I'm talking about. This is a planar system, and every atom is shown its magnetic moment oriented in a particular direction. And look at the homogeneous orientation of all these magnetic moments in the system. And this gives rise to a very special kind of magnetic texture, magnetic structure. And if you have, instead of two-dimensional structure, let's say complete three-dimensional structure, you can also have projection of the such magnetically oriented, let's say, structure along the third direction, giving rise to some very interesting pattern where the magnetic moment orientation is very specific, and you can also identify this as a magnetic particle. So this is called as a skirmion. Skirmion is a very local, very stable, and if you solve this particular problem, magnetic problem, in a nonlinear field theory, you get a solution as a soliton. So you can safely consider this as a particle like an object. However, this is interesting because they are topologically protected. So maybe the community who is listening me today, if somebody is interested in topological materials, topologically protected materials, whose Chern number is non-zero, whose some properties, let's say spin Hall effect, topological properties, they are very interesting. This is one of the most interesting problems to solve for right now because people are pursuing very seriously. Look at here. So if you take a rotation along a circle where these magnetic particles are located and they vary their magnetic direction. So if you take one complete rotation and you see that there is no change of rotation, then you can say that a particular number order parameter, that circle, one angle, magnetic vortex is completely zero. But if the magnetic moments rotate and they take one complete circle, in that case, you have very similar analogous to Chern number, which is equal to +1. They are topologically protected particles. If you go for another way around, you may have two different or maybe negative rotation where the Chern number or the rotation number gives as a -2. You may have multiple integral numbers as well, which is +2, +3 as well. You may have half integral numbers as well, which are still important in topological point of view. And here are some important textures that you can certainly find in a lot of papers, and these are experimentally proven. Here is one experimental picture. Look at the size of 20 nanometers. And people, by using scanning tunneling microscopy, spin polarized tip, they can use and scan the entire sample and identify there are certain textures which can be identified and located and can be utilized in a lot of different properties as well. They are called as magnetic skirmions. And based on the orientation of magnetic moment, as you go from the center to the other direction radially, you can find out the way they are rotating. You can say they are block skirmion, they are nil fermions, they can be some other names as well. They can be anti-skirmions, they can be solitons, some other properties. And again, at the root, we again take this physics to the same that we were discussing some time ago. We have one atom having a spin oriented in one direction, another spin oriented in another direction, and there is a necessity of inversion symmetry breaking environment, which is coming from very large spin orbit interaction. So spin orbit interaction plays really important role here, where the quantization between the orientation of spin and the orbit, it contributes to the energy of this entire system and makes such kind of chiral structures or non-homogeneous or homogeneous but non-coordinate structures stable and gives some kind of interesting properties. So here is one very summarized picture. Let's say if you bracketed all the numbers as in the order of, let's say, topological number that we are getting out of this particular skyrmion, vorticity and the helicity of the spins. They are related to each other. We can identify different skyrmions as well. So we can have meron, we can have antimeron, we can have skyrmion, skyrminium, then we can have let's say block or nil skyrmion as well. They all differ from each other only by the orientation of spin with respect to each other. And depending on the kind of skyrmion we are getting, we may have different interesting physics hidden in it, which can be utilized for spintronic properties. And you'll be surprised to know, okay, we know right now some technologies where we use writing the data right now. So if you can recall again, the way we write the CD drives for computer or the pen drives, right? We have magnetic material. All we use mostly those materials or those elements in those pen drives or USB drives or memory drives where perpendicular magnetic anisotropy is more prominent. So mostly those magnetic moments are oriented perpendicular to the surface. We have a magnetic pointer, right? Magnetic pointer usually scans through that particular material. Based on the applied magnetic field, this pointer, they flip up or down. And based on that, we either store that particular information as 0, 1, or we try to again retain the magnetization back so that we can have rewritable medias as well. But looking at those, we need magnetic domains in those materials. We basically need larger and larger magnetic domains so that we have better and better accuracy. Now look at this. We have such kind of skyrmions where we have here iron, single mono layer of iron in a triple layer of substrate or double layer of substrate, or even like something like that. And you see that by scanning tunneling microscopy, we have observed such kind of skyrmions. Now they are not spherical skyrmions or circular skyrmions, but they are let's say non-symmetric kind of skyrmions, where if you look at the atomic scale, if you model that using model Hamiltonian and try to plot, try to find out at what energy these particular magnetic moments can be oriented in a specific direction in the space, we can plot it. So look at here. So this is a scanning tunneling microscope. We have a tip. Again, the tip is having some kind of the atom at the tip, which is spin polarized, and we can change the field, we can change the orientation of the atom, the magnetic moment of the atom which is attached to the tip. And the moment you change the voltage here of the tip, let's say -3 voltage, you actually delete one skyrmion here. If you can look at here, right? This was one skyrmion here. After you apply the field, which is -1, you have almost deleted this skyrmion. There were 4 skyrmions located here. There are now 3. If you scan this in a two-dimensional plane and again apply the same kind of negative field, you actually can delete. What do you mean by delete? We actually try to realign all the magnetic moments on the surface atom again back to the plane, right? So we can still change the magnetic texture of that particular surface, and hence we can delete those atoms. We can actually write the magnetic skyrmions again by changing the polarization of the magnetic tip and see the effect. This is very easy to use as a data writing. And look at the size of this particular system, hardly few nanometers. We are, if you remember, I think most of the people we have witnessed the floppy drive having 1.44 megabyte, or even a CD drive with some 500 MB or 1 GB as well. Pen drives right now, we have 1 terabyte right now here. But even a few nanometer or few micrometer size, we can store few terabyte, petabyte of data if you have such kind of control technology, where we have control on flipping the magnetic moment direction in this particular sample. Again, another one. We can also use this skyrmions as a switch. The moment you change the polarization, the moment we change, let's say, the applied voltage, we can also switch a particular skyrmion to on and off state as well. Again, there are a lot of different experimental setup here, which I'm not going to discuss in detail right now. But still, it is possible that we can use those magnetic particles as a switch. And again, look at the size of the switch that we are having. We are talking about few atoms as a group, few atoms in a skyrmions, which treats as one switch. And we can have so much of control. We are actually talking right now about quantum computing. We are talking about some extremely super fast computers in miniature size devices. So these devices will play very vital, very important role if you have a good control on those skyrmions magnetic particles with the help of just applied field or with the help of just STM tip that we are having. Again here, the moment we try to just flip the electric field, we see that this skyrmion is actually rotating. We just like we are rotating a circular object, right? The moment we put on the field and off the field, these fermions, they appear like a bubble, and we have control on even orientation of this entire fermion. Again, the point that I would like to say here, when we say that we are rotating these fermions, we do not mean that we are rotating atoms. The atoms are stationary. Only the magnetic moments aligned, or they are representing that particular atom. We are only changing the direction. They are extremely stable. These all experiments, they are tested close to the room temperature as well. So the future is really near, that we can change all this device technology, where all the spintronics devices actually, where we have control on orientation of magnetic moment on an atom, to a particular technology where we can use either in storage or memory devices, or even read and write or electric switches. You can imagine the entire semiconductor industry can be replaced the moment we have proper atom, where we can decide what atom should give what magnetic moment. Let's say the rare earth, or the lanthanide series elements, or actinide series elements, or conventional magnet, nickel, iron, cobalt, and which substrate that we are choosing, and the amount of voltage that we are using. So if we have this all control, it's very easy that we can transfer all the existing spintronic industry to a new set of industry where we have a lot of control here. I mean, no wonder that people are investing a lot in these days on rare earth materials, because their magnetic properties is extremely fascinating. Their ground state itself is non-collinear, and because of that, it's very easy that you can mold those non-collinear magnetic moments in a specific way, in the way we want, in a particular device as well. I think my time is almost over. The last slide here. This is also used. I mean, this is one of the example of using this carbon as a switch, where you can change the orientation of magnetic moment by with the help of the external electric field, or the uh, electric voltage. Here it is like reading and writing. So it's a racetrack memory, a classical example of racetrack memory. And this is the paper that I have referred right now in 2023. This is the experiment which was performed in one of my groups in Germany again. This was laboratory tested at room temperature racetrack memory, where you can actually store in terms of the store information in terms of 0 and 1 by switching on and off, uh, let's say, these fermions. Can you imagine that people have already started thinking about using these fermions, even in the synapses, neural synapses, where the information needs to be transferred from one synapse, one neuronal cell to another neuronal cell. And again, the detailed experiment is done looking at these statistical error bars as well. They are so prominent. They are so clear, crystal clear data people are getting, that this can be used to pass the information from one cell to other cell as well. And looking at the way this is growing, not only spintronic industry, but medical industry may also get a lot of benefit because of such kind of particles. I think I'll stop here, but I'll be more than happy to discuss and get some questions from audience.
Yeah. Thank you. Thank you. Very nice.
Thank you, Vikas sir.
Let's take few questions from the audience.
Sure.
Audience, if you have any questions, please unmute yourself and you can ask the question.
Dr. Vikas, I would like to ask one question.
Please, sir. Please, sir.
Yeah. So whatever you have discussed just now, actually these things are very new to us. I think this all in the research level. Whatever things you have discussed now, it is in the research level. But when it will come into the practice, that means in the quantum computing, this thing will be easily applied and output will be good. So how much time it will take to come on that?
Yeah. So people have already started. I mean, to be very precise, after 2020, this has taken a very fast pace. And I expect by 2030 or 2035, most of the devices will have such kind of magnetic particles implemented. Because on in the laboratory, a lot of things are tested in different grounds, and they are tested very well. They are very stable at room temperature. They are very stable against various changes in the external magnetic field, because we have to have some kind of device that sustains for longer time. It is very robust. It is fully in human beings' control. It shouldn't happen that there was some kind of external field randomly, which we intentionally did not want to interfere, and still our device has got some kind of weird numbers or some strange numbers to come as an output. But people have tested this, and a lot of things they are coming as a good result. So I expect that within 5 to 7 years time, this will be starting reflected in the real life scenario.
Okay. Thank you. Thank you. In the audience, there is IIPT President Dr. P.K. Aluwal is there. Dr. Rekha Ghorpade ma'am, Secretary is also there. If they want to add something, please.
Yeah, even comments are also okay.
There is a one question in the chat box.
Yeah,
In
I'm just
medical,
opening that. Yes,
yeah,
yes.
please.
Yes. So in medical industry, how it use quantum to store the data and pass to other, and how to coordinate the term with physics and radioactive physics, etc. The question is asked by Dr. Lekha ma'am. So to tell right now, because this stores information, as I discussed in this slide, it stores the information. Um, it is very important that, let's say, for example, now the synapses that we are talking. So basically, when we talk about the signal transmission in a neuronal cell from one cell to other cell, we know that it's a typical action potential which goes from one cell to another cell. And action potential is a very specific function of the voltage, or the specific function of, let's say, change in the potential as a function of time. So this particular information can also be reflected or maybe imprinted on a skyrmion or a magnetic particle. And this magnetic particle, even if it is a solution or even if it is some kind of fluid, it can reach from one neuron to another neuron. Now, obviously, this is supposed to be considered for the treatment of those patients where the signal transmission is not happening really well. But this magnetic particle, if they are very sturdy, sustainable to the environment which is there in the synapse, they can carry the information from one neuron and they can actually land up with another neuron and pass the information, where another action potential can be triggered on another neuron, which is taken ahead for the signal transmission. And being very quick responsive, this is also very easy that we can understand the total time span between the signal transmission between two neurons is very, very short. This is in milliseconds as well. So they are perfect neurotransmitters, I would say, neurotransmitters which we can replace artificially. So people are right now doing this as an AI, using AI, this experiment, how fast this can be used to transmit signal from one neuron to another neuron and so on.
Shashikant sir, over to you.
Yes, sir. Thank you. I request Ahalwale sir, please, your few words on this today's session.
Okay, thank you very much. I think,
2025. So please
can you
sum
hear
up,
me,
sir.
please?
Yes,
Yeah, yeah,
yes.
yeah, really.
Okay,
Yes,
lovely.
sir. Yep.
Professor Vikas, it was a wonderful lecture,
Thank you, sir. Thank you.
and it reminded me of 80s when I was working on Kondo problem.
Yes.
And our Gita was this 5 volumes of Rado and Suhal, if you
Yes.
have seen those volumes. And this RKKY interaction and all those
Yeah.
things. So nicely those have been done there. And it's a very difficult topic, actually. Magnetism is a very, very difficult topic. It's not an easy topic.
Yes.
The stage at which you spoke, actually, it requires years to really understand things and reach that kind of a stage. Hats off to you. I
Thank you, sir.
think when I was listening to you, I was just wondering that these are the purely quantum mechanical phenomena. I mean, here is quantum mechanics is in full play right from the very beginning. If we talk about magnetism,
Yeah.
when we used to study it in the college, we never used to even touch where the quantum mechanics comes. But then suddenly, when you start, looking at Keeter's book, you find the origin of all this is in quantum mechanics, and that Heisenberg's interaction comes into picture.
Yes.
And that Dzhirinsky Moria thing which you talked about, there was another book which was like a Bible for us by three authors of Russian origin,
Mhm.
quantum field theoretical methods uh, quantum field theoretical methods for statistical mechanics, actually. Abrikosov, Dolinsky, and there was third author who was there in that. And it used Feynman diagrams actually to do all those kinds of calculations, etc., etc.
Yeah.
I was
Yeah.
just wondering if we can really think of creating some kind of a course which can really be done on IEPT platform, maybe say 30 lectures, where we
Mhm.
bring more depth into all those things which you talked about, because
Sure.
normally these things are never touched in courses in colleges or even in the university departments.
Yeah. Yeah.
You are a person both theoretically sound and also experimentally looking at all those things with latest electronic structure calculations also. So it is a high time that if we can take lead and train students in looking at these beautiful Hamiltonians, see that how they work in explaining different phenomena, the way you explained that they are the happening things now. Uh, there is you know that giant magnetoresistance
Yes.
phenomena change the technology in a very big way.
Yes. 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 That's
And
true.
when this Nobel Prize was being given, somebody asked that why you are giving these theoreticians from France the Nobel Prize. And then somebody in the Nobel Committee said, look, we give Nobel Prizes for the basic phenomena. The person asked that, look, there are people sitting in the uh, big labs like IBM and such things where they have really converted these into small memories. Why you are not really celebrating them? Then the reply was they would have not been able to do that technology if this kind of a phenomena had not been discovered. So that
Yes.
was just great. And I think magnetism is a great subject. I wish more of our people start studying it theoretically, because I may be wrong in making this perception. We are losing our edge in India on theoretical physics because people are not coming to study theoretical physics now. There is a lot of time which is needed to even get hold of the basics, and people want to run away with a degree which they would like to have in 2.5 years or 3 years. And this requires a lot of patience, perseverance, effort to do PhD in this area. But Professor Vikas, you are a student of Kanunge sir. Please think about
Yes.
it if we can really imagine doing that kind of a course. That will be a nobility, I think, in
Yeah.
this era.
My pleasure,
And
sir.
maybe
Thank
we
you.
can also train people on, if they don't understand even the basics, we can bring in these
Yeah.
electronic structure calculations of these systems and they can be trained on those also. So I really enjoyed
Certainly,
it.
sir. Thank you,
First, I
sir. Thank you.
watched you on the YouTube, then I switched over to the Zoom. And it has been a wonderful, culmination of a program which IAPT did this year, right from the month of January. Every month we were having webinars, and I think the level of this webinar was really research level. Earlier webinars were touching upon historical aspects and those stories which are very fascinating and easy to convey. But this set of lectures were just wonderful. I want to congratulate this RC, sub RC Pune, that they have done it and they have done it with a thumping success, I would say. So this is great. So Dr. Vikas, we will be in touch with you and let us plan something big,
Sure, sir. My
right?
pleasure.
Uh,
It's really
Thank
honored
you.
to have your words. Thank you, sir. Thank you, sir.
Thank you. So,
Thank you.
so wonderful frontiers you brought in front of the audience here. And we will try to convince people that please watch this lecture if you want to hear about that, why China is after rare earths and
Yes,
USA
yes.
is after rare earths, and why this Ukraine war is going
Yes.
on. And
Certainly,
Trump is
sir.
actually trying to put his hand on all the rare earths of Ukraine. I mean, that is the kind of story which technology brings to the table, which sometimes we don't realize that how important this is. And that is where people start respecting physics and physicists. So thank you once again. Thank you very much.
Thank you, sir. Thank you so much.
Thanks a lot.
Thank you, Halwani, sir. Thank you so much.
Thank you, sir.
So,
Yeah. Rekha ma'am would like to say something.
Sir, good evening. It was really a wonderful lecture, actually. In
Thank
fact,
you.
initially, he reminded me of my MSc days also. Of course, all those calculations and became a very nostalgic. And slowly, he took us to the recent developments. I think this skirmions and all is a very new thing which I learned today, in fact. And the very minute analysis has been done by our president, sir, also. I think he is the one who always generates the programs when he attends a session. And as he has suggested that the course on such kind of quantum uh, mechanics and the developments would be really advisable and will be beneficial to all of us, not only students, but even the teachers now. A teacher like me who is retired is also getting a benefit and understanding at this level. So thank you, Dr. Vikas, for such a wonderful lecture.
My pleasure.
And on behalf of my personal behalf, as well as on behalf of IAPT, I extend a very warm gratitude to you. And
Thank you.
I also feel that this is the beginning of your association with Indian Association of Physics Teachers. It's we are just trying to connect with people, and they will be with us throughout our journey. And
Sure.
you will definitely add to the values to the IAPT programs. Thank you for
My
joining,
pleasure
and please
to be part of this
be with
family.
us. And
Sure, ma'am.
thank you, Dr. Kangude, for having such a wonderful session by your student, and the RC0 Sub-Regional Council 08C Pune, Manisha Madam and Shashikant Sir also for having
Yes.
such a wonderful series. As Sir has already said that we have started it in January, and we are now ending with very very good sessions by Pune RC. So I'm proud of it. And we keep this
Thank you
work
so
going
much,
on
ma'am.
further also here. So thank you.
Yes.
And I suppose we have generated few programs through this series. Those who have missed this particular series, please go to our YouTube channel, Central IPT, and have the benefit of it. Thank you so much. Thank you, Kangude sir, Manisha madam, and Shashikant sir.
Thank
May
you
I
so
just
much,
add one
madam.
thing?
Your words
May I
really
add just one
inspire us.
thing? Dr. Vikas, I
Yes,
don't
sir.
know whether you are a member of IAPT or not. I would request you please become a member of IAPT.
It's my honor to be part
And
of this.
we have yes, we have a very dynamic website. You just go there,
Sure,
put up
sure.
your profile, and I
Yes.
would request you to become our life member,
Sure,
because
sure. It's
people
my
like
pleasure.
you can bring lot of rich content to our members.
Certainly, sir. It's my pleasure.
That's
And
very important. We are also targeting young students now
yes,
through workshops, etc. There is
Yes.
already one workshop going on in Maharashtra,
Yeah.
in Kolhapur University.
Sir,
So
there
that is a
are
very interesting
two.
thing which is emerging.
There are two.
Yeah, there
Two
are two
winter
winter schools.
schools.
We are so
And
proud of
Dr.
Maharashtra
Vikas,
Maharashtra
let me
is,
is
tell you,
yes.
no other institution must have done these kinds of lectures in the country. This was just a fascinating year for us,
Yes, sir.
I
for the physics
feel
students.
very proud that the Mumbai Sub-Regional Council is conducting both these winter schools at Ratnagiri and Kolhapur. So the model which we have started as a summer school in Mumbai
Yeah.
is really working very well. For last 9 years continuously, that summer school has been taking place. So I think
So now we
Pune
have summer
also will
and
join.
winter school, ma'am.
Yes,
Now we
yes,
have summer
sure,
and
sure,
No,
winter
ma'am.
school.
the model which we implemented as the
Yes.
summer school, I think that
Yes,
this
yes.
is an extension that we are having the winter school now. Yeah.
Mhm.
Yes.
So once again,
We'll
thank
also,
you,
sir.
Professor Vikas.
Yeah.
See you
thank you, sir.
again and
Thank
again.
you. Yes, yes. Thank you, sir. Thank you so much.
Thank you.
Thank